Alright folks, today let's do Leetcode problem 215. The kth largest element in an array. In this problem, we will use an algorithm called quick select. It's very similar with quick sort, except for quick sort its time complexity is O(n) times log n. But here quick select is normally O(n). So let's see how it works. So in quick select, we do partition first. We do partition first. Use a partition function. So use partition function. Okay, partition function will do two things. The first is to sort the array as a whole, sort the array as a whole. And the second is to return the pivot position or pivot index. Sort the array as a whole, meaning on the left all numbers are less than the pivot value, while on the right is larger. Okay, so the partition function does two things. So using the partition function, we can get the pivot position, and we can also sort the array based on a pivot value. So there could be, if the kth value, we want to find the kth largest, then if k minus 1 is less than the pivot position, well, that means the kth largest should it's not easy to understand, but in partition function, maybe since we are looking for the kth largest, so maybe we should sort the array as a whole, meaning on the left all the numbers are larger, should be loaded that are larger than the pivot value. So in that way we can solve this problem easier. Okay, if k minus 1 is less than pivot position, then the kth largest should be on the left. Then we should search on the left. If else, then we search on the right. So that's how it works. If else, then we search on the right. So let's try to find the time complexity of this algorithm. So in this algorithm, each comparison we need to do a partition function. The partition function has a time complexity of O(n), and after the comparison we search on the left, which is different. Then we don't need to search on the right, which is different from quicksort, in quicksort we need to search on the left and we need to search on the right. Not search, but sort on the left and sort on the right. So in quick select we only search on the left, we totally ignore the right part. So so on the next comparison then we on the next comparison we do another partition function which operates at O(n) over 2. And then on the next one, then we operate at O(n) over 4. So the total time complexity is O(n) plus O(n) over 2 plus plus O2 plus O1. So what's the time complexity of this? It's really hard to intuitively look at it. Maybe we will guess O(n) squared or something like that, but really it's not, or O(n) times O log n, but really it's not. How to calculate it? There's a good way to calculate like this. So we say the overall time complexity is OX. So then what is OX? So in order to find OX, we use OX times O1 plus O1. Then OX plus O1 is really this plus O1. So it's really O1 plus O1, which is this one, plus O2, which is this one, plus O, and so O1 plus O1 equals O2, and also O2 plus then O2 plus O2 equals O4. O4 plus O4 equals O8 plus, then the whole thing plus together equals O(n), then plus O(n), that equals to O2n. So that means OX really is O(n). So it's a little surprising that this algorithm gives us overall time complexity of O(n), but it is indeed the case. Let's try to implement this algorithm. So let's do the corner case first. Return non-nums, return nums. We use quick select function. Quick select function should return us self dot quick select function. Okay. Similar with quick sort, we need to define the starting point and the end point as of nums. Define quick select and okay, if the end of the recursion is start larger or equals to end, and return pivot position equals the partition function. Maybe we should write the partition function first. Let's write the partition function first. Find partition so the partition function should do two things: sort the array by pivot value and return the pivot position. Sort the array by pivot value. So we need to define the pivot value. We just define the pivot value as j. We should note that we should sort the array in descending order instead of ascending order. So meaning that on the left the numbers are larger than pivot value. So on the right the numbers should be smaller than pivot value. So this is very similar with quicksort algorithm. We should note that this should be less or equal than the pivot value. Now that array I has been changed, change the array from I to pivot value, and then return I. Okay, that's partition. So we find the pivot position using the partition function. And then compare the pivot position with k minus 1. If k minus 1 is less than pivot position, then we should search on the left. Return. So quick select, return large case, not just element in array. So return case largest element in array. So we should return self.partition array, the left part, pivot position. If k minus 1 is larger than pivot position. If k minus 1 is larger than pivot position, then we should search on the left, on the right. Not partition, but quick select. Okay. pivot position plus 1 and then k, else if k minus 1 equals the pivot position, then we should just return the pivot position. We are going to return the largest element, that element, not the position. So alright, okay, that should do it. Let's see. Quick select. Okay, there's a typo here. Okay, looks good. Output is none. Oh, okay. So if start equals end, wait a second. Something is wrong with the recursion. If the start equals end, then we should return the array start or array end. So that should do it. Okay, good. So as you can see, the runtime is pretty long, because even though the time complexity is on average, but in worst case it's really O n squared. If we say, you know, you will select the pivot position, array I is always the smallest or the largest number, that will lead to worst case, so which leads to a time complexity of O n squared. So actually there are better ways to solve this problem, or this kind of problem. Find the case largest element in an array. If we want to find the case largest element, or you know, or try to find case smallest element, or whatever case something element, you know, we can always try to use a method or a data structure called heap. In Python, a heap is a minimum heap. So it always it uses the tree and always store the element in a order, so that you can add an element into the heap and maintain the order in O log n time. And also, let me make a note on it. Add page. So this page, we use heap. This page, we use selection sort. So okay. So for heap, the add an element and maintain the same order operates in O log n time. Also pop also operate in log n time. Also delete or insert, delete, say delete, insert is add, also operate in log n time. So if we have a heap, then we can keep track. Then we can keep track the largest number. We can always keep track the largest number, and then we know the case largest number by keeping the heap size to be k, then the let me think. So if we keep every element in the heap, so we keep every number in the heap, every number in the from the numbers into the heap, then in the heap, the top one will always be the smallest one, and this should be the largest one. Okay, so when we keep lumps into the heap, we always want to keep the heap in the size of k, so we always pop when the length is larger than k, we pop the smallest one. So in that way, when we iterate all the numbers, the final k length heap will store all the largest number. So the smallest number then will be the k's largest number. Then we can just pop it out. So let's try to implement that algorithm. By using the heap. So firstly we need to import a heap q. Import a heap q. Then we create a heap. Then for nums, iterate the nums and put the nums into heap. So it's heap q dot heap push nums, put num into nums heap. And also we want to keep the size of the heap. We want to keep the size of the heap less than k, less or equal than k. So if it's larger than k, then we pop it out. Oh, we pop the smallest out. So also we are going to use a method in heapq. Heapq dot pop heapq dot heapup. Interesting, heapup. So then pop the smallest number in the nums heap, and then after iteration, the k size heap should store all the k largest number. So what we need to do is we just need to pop the smallest number, which is pop nums heap, and that's it. Let's hit run. Wait a second. Oh, we didn't return, so this should be return. Just click submit. On incident does not match any level. Oh, okay. So this is making something unhappy here. That's good. Okay, good. Okay, good. So if we compare the runtime of using a heapq with the selection sort algorithm, the selection sort algorithm uses 1 second, and the heapq uses tens of milliseconds, which is much faster. This is because even though quick select is supposed to have on time complexity, but that's ideal case. In many cases, or in worst case, it's on squared time complexity. However, in heapq, add and pop are all operated in on, are all operated in O log n time complexity. So in this algorithm, so each pop is O log n. So we pop each pop is O log k because the length of the heap is k, so each pop is O log k, and during the iteration it's O. During the iteration of nums, the time complexity is on. So overall, it's on times log k. So it's O. The overall time complexity is on times log k. This is very important. Okay. So that's all the video for today. Thanks for watching. If you like my video, please upvote it or subscribe my video channel. I'm trying to update at least one very typical, very important problem, Leetcode problem every day. So if you really want to like it, you really want to support me, please click subscribe or share my video with your friends. Thank you very much. Bye bye.